experiment. And first of all, I would like to thank the organizer to give me a chance to talk in this so nice and workshop. And today I will give a talk about the structure of the hydrogen 7, which is a very new result. Okay, and so that they are my collaborator and Razaskas and Carbonell. Okay, and here is my outline. And after introduction, I shall talk about hydrogen 5 within the framework of the triton plus 2 neutron. And after that, I will give a talk about hydrogen 7 and within the framework of the triton plus 4 neutron state. Okay, so first I would like to explain about some motivation. Why I studied hydrogen 7. Okay, because maybe you may know in 2016, we have observation of the 4 neutron state by RIKEN in 2016. And so according to this experiment data, now, and here 0 means the 4 neutron breakup threshold. Within this 4 neutron breakup threshold, so they reported the energy is like this. So that means that they reported that this energy is from boundary region to the resonance state region, like this. So if this observation is reliable, now we have no isotope nucleus. So then after this observation of the tetraneutron state, now immediately we motivated this calculation with these people. So then in 2016 means that here I talked to at the KITP workshop in 2016 in this workshop. Here and at this time also the organizer is also Chris Green. And then after this workshop, and so many people are motivated to calculate the tetraneutron state. So here is a summary of tetraneutron state theoretically. Now, and also so far, they have some positive result, and also they are not so positive result, but not so negative result. And after that, so I calculate this tetraneutron state using my method, using the AV8 potential, but at this time we have no resonance state. And after that, also Deltuba and also Chris Green calculated this and tetraneutron state with each different method, and also they had no resonance state for the tetraneutron state. Therefore, currently, now in the world theoretically, we came to almost negative conclusion that means no resonance state of the tetraneutron state. However, so if we have resonance state experimentally in the future, how do we understand this tetraneutron state? So now we just changed the idea. Let's put on the triton to this tetraneutron state. That is a hydrogen 7. And then this hydrogen 7 is also composed of the 6 neutron and 1 proton. And we call this system as a super heavy hydrogen. Now we have a question. This hydrogen 7 is bound or resonance state or nothing. So we don't know theoretically. So now let's explain about the hydrogen isotope before talking about the hydrogen. Okay. So maybe all of people knows that the lightest isotope is just hydrogen. So this is experimental data. Now we know the deuteron is the lightest bound nuclei. That means this is binding energy is minus 2.22 MeV with respect to neutron proton breakup threshold. And we can add it to one more neutron, this is a deuteron, then this is a triton. And then this is experiment data. And also one can add it to one more neutron there, and then this is the hydrogen 4. And these are the experimental data. And also we can add it one more neutron, and this is the hydrogen 5. And almost 20 years ago, they observed hydrogen 5. Okay. And then according to the experimental data, this is the energy. And then so that they reported the energy is around 1.7 MeV with respect to the triton plus 2 neutron breakup threshold. And then this is the decay width. Also from here, we call this nucleus as a super heavy hydrogen. So, however, after this experiment data, also several experiments reported about hydrogen 7. Okay, I summarize the experimental value of the hydrogen 5. Okay, this is the Koleshenikov experiment data, which I already showed you. And after that, they measured experiment like this. Okay, this one the energy with respect to the triton plus 2 neutron breakup threshold, and this one the decay width. You can see that energy is almost similar with each other. However, the decay width is dependent on the experiment like this. This is the current situation of hydrogen 5. And then in 2007, also we have a new data by this person, and they reported the energy of hydrogen 5. Energy is also 2.4 MeV, and decay width is around 5 MeV, which is so broad resonance state for the hydrogen 5. Okay. This is the current situation of the hydrogen 5. And how about hydrogen 7? Okay. Here is also almost 20 years ago, we have observed data of hydrogen 7. And according to this experiment data, they reported the energy is like this. Okay. They reported the energy is almost 0.5 MeV with respect to the triton plus 4n breakup threshold, and the gamma is so narrow. Okay. So then if we have a narrow decay of hydrogen 7 at lower energy, then maybe there could exist have heavier hydrogen isotopes such as hydrogen 9, something like that. Okay, so now we have a question. What is the limit for the hydrogen isotope? Probably hydrogen 7, or we can go beyond. We have no idea. So, and then, so this is the experimental situation. Now I will explain about the theoretical calculation for hydrogen 5 and hydrogen 7. Okay. So far also 20 years ago, Timothy et al. Calculate the hydrogen 5 and hydrogen 7 using the Volkov-NN potential and within framework of the hyperspherical harmonic method. And according to her calculation, she reported the energy of hydrogen 5 to be the 1 MeV above the TNN breakup threshold. And also, and she calculated hydrogen 7, and so she reported energy is a 3 MeV above the t+4n breakup threshold. So in this way, she calculated energy with bound state approximation. Then, however, she didn't give any decay width for this nuclei. After that, so Japanese colleague Aoyama-san and Itagaki-san also calculate the hydrogen 7 using the same NN interaction like her, and then within the framework of AMD calculation. And according to their calculation, they reported the energy of hydrogen 7 is a 4.2 MeV above the threshold. However, also they did not calculate for the decay width. And also they had no report for the energy of hydrogen 5. And very recently, last year, Lee et al. Calculate the hydrogen 5 and hydrogen 7, and using the Gamow-Fischel model calculation, using the Minnesota NN potential. And they predict the energy of hydrogen 5 is a 1.4 MeV, and the decay width is a 0.5 MeV. And also they calculate hydrogen 7, and so they reported the energy of hydrogen 7 is a 2 and 3 MeV with respect to the triton plus 4n breakup threshold, and the gamma is a less than 1.1 MeV. So in this way, they predict to have very narrow decay width at the lower energy with for the hydrogen 5 and hydrogen 7. Okay, so now what is the experimental situation? Now recently, so this reaction has been done at the RIKEN RIBA factory. And then now this RIKEN proposal number is like this, and then now analysis is still ongoing. So now, so in this situation, now it is timely to calculate the hydrogen 7 to obtain the energy and decay width theoretically. So motivated by this situation, we study the hydrogen 7 structure within the framework of the Triton +4n 5-body problem. And also, we also discuss on the energy and detail width of hydrogen 5 within the Triton +2n 3-body problem. So now, almost we submit this paper to the physics letter B during this stay in KITP, then we should have acknowledgement to the KITP workshop. Okay. So then, now this is a framework. Okay. For the NN potential, we took the Minnesota potential, which composed on the only central potential. And for the, also we should use the Triton and neutron potential. Okay. For the, in this case, now we took this experimental data. Namely, one was my collaborator, we must so make this kind of potential. Okay. And so for this potential, he calculated phase shift analysis like this. Okay. P wave is like a little bit so attraction, and then but so due to the Pauli principle, now S wave are repulsive. And then and also, so this potential two-body calculation is compared with the four-body calculation like this. Okay. So then you can see that so this two-body phase shift resonance state is almost consistent with the calculation by four-body calculation using Malfritton potential. So plus, also we introduce the phenomenological three-body Tn force to obtain the energy trajectory of hydrogen 5, and so defined by this equation. Okay, this is a one-body, one-length Gaussian potential. And here, V0 and range of the Gaussian potential, this V3 are free parameter. Then these two are fit so as to reproduce the data of the hydrogen 5. So then, two-body NN interaction plus Tn two-body potential plus three-body potential, and we apply to this three-body model. Now, using this potential, we take the Gaussian expansion method, which is developed by Kyushu University group, namely Camille and his collaborators, including myself. And this method has been applied to the high pressure calculation of the various 3- and 4-body systems, such as the exotic atom system and so on. Okay. Here, I will explain about the 3-body problem very briefly. Okay. In order to solve the 3-body problem very accurately, we take these 3 kinds of Jacobi coordinates. And then we should solve this Schrödinger equation. Now, Hamiltonian is written by like this. And this is the kinetic energy and defined by this equation. And so this V1, V2, V3 is just so consistent two-body potential defined by this coordinate. And then this phi 0 is defined by this and summation of these 3 kinds of Jacobi coordinate. And for the each channel are described by this and spatial part. This is a small r, and this is a capital R part. And this spatial part are defined by this product of this radial part plus product by this spherical harmonics. And here is unknown coefficient, and this unknown coefficient is determined by diagonal Hamiltonian. So then this each spatial part, this radial part are described as this Gaussian form. And here is this mu r is a range parameter, and the range parameter are taken by geometric progression like this. So then, using this basis function, we calculate this matrix element for each. Then, by solving the generalized matrix element, matrix eigenvalue problem, define this equation, and we get the energy E and non-coefficient C, like this. And then we can get this set of the wave function and also set of the energy value, eigenvalue. Okay. So then, so it should be noted that the hydrogen 5 is resonance state. So therefore, in order to obtain the resonance state of the hydrogen 5, here we use the complex scaling method. Here we have the radial part for the small r and capital R. Then we scale to the for each by exponential I theta for each. Then, and this theta is a scaling parameter. Then after diagonal Hamiltonian and the scaling parameter theta, then we can so rotate like this. So then if we have energy pole as a resonance state, then so pole is stable as a respect to the rotation parameter theta. Then here is a resonance state. So in this way, and we can get the energy pole of the hydrogen 5. So now, and here is again, so this we use the 3-body force. So, and then V0 and V3 are just free parameter. Then so as to just we should fit the so as to reproduce the data of the hydrogen 5. However, we have a question. Which experiment data of hydrogen 5 should we fit? Because as mentioned before, this is a list of the hydrogen 5 experimental data. You can see the energy is almost similar around the 2 MeV. However, decay width has you can see the variety. So then which data we should fit? So then currently we have no idea. So therefore we use the data like this. Okay, this is just calculational result by Limas within the 5-body program using the Faddeev-Jakubowski method. And then these are the realistic interaction. He used 3 kinds of the NN realistic interaction, and he did the calculation of the resonance state of the hydrogen 5. And then this is the energy, okay? And the energy is around the 1.7 to the 1.89 MeV with respect to t+n breakup threshold, and the decay width is around 2.4 MeV. So now we take this result, theoretical result, as an experimental data. Of course, so that we can compare this calculation result with the experiment data by Kolesnikov. And as you can see that this is the first measurement by Kolesnikov et al. And which is close to this Limas calculation. But in any case, we take this result as an experimental data. And what's happening? Yes?
All these leaves are the same?
Yes. Please ask to Limas. Yes? But here is the error. Where is the Limas? Disappear. Yes. Okay. So what's happening? The energy trajectory of hydrogen 5. Okay. I will show you the result first of the hydrogen 5 using the 3-body force. Okay. I will tell again this V0 and V3 are free parameter. Okay. So then you can see that energy trajectory of hydrogen 5. If I take the V3 equals 6 femtometer, and here is the energy trajectory. And this value, each value is a V0. Okay. So then if we use a V0 equals 2 and V3 equals 6, then energy trajectory of the hydrogen 5 is like this. Okay. And this green is experiment data by Kolesnikov experiment data. And you can see this blue small one. This is a Limas calculation. Okay. So then we can compare these 2 data. Then in order to fit the experiment data, this blue one is better. That means V3 equals 8 femtometer. And if we have V0 equals 2.5 or 3, and then our result is close to the experiment data. And also if we take the Limas calculation result as the experiment data, the 2.5 is best fit. So then if we have this value for the 3-body potential, then So what is the energy pole of the hydrogen 7? So then this is the framework of hydrogen 7. Okay. So we take the same Hamiltonian as the case of the hydrogen 5. Then this is the 5-body calculation, and we take the many kinds of the Jacobi coordinate, and totally I take the 120 Jacobi coordinate like this. And then wave function is written like this. This is the isospin part, and then so this total isospin equals 3/2. And then total isospin and J like this. So then each basis function is like this. Okay, we take the Gaussian for the radial part like this, and this is the range parameter, and we take the Gaussian progression for the Gauss range. Okay, this is for the small r, but also similar for the capital R and rho and S. Okay, and then we solve the this Schrödinger equation, and then by the diagonal Hamiltonian, now we obtain the n eigenvalue for the each j pi, and for the hydrogen 7, we input j equal 1/2 plus state. And here we use almost the 56,000 basis function. Therefore, after diagonal Hamiltonian, we obtain this 56,000 and eigenfunction for the j pi equal 1/2 plus state. So then for the calculation of the hydrogen 7, it is difficult to apply the matrix complex scaling method for the 5-body calculation. Therefore, for this calculation, I use the real scaling method. What is the real scaling method? So this method is often used in atomic physics. So in this method, we artificially scale the range parameter for our Gaussian basis function by multiplying a factor alpha. For example, we scale the alpha equals 0.8 to the 1.5. And then repeat the diagonalization of the Hamiltonian for many values of the alpha. For example, this is a schematic illustration of the real scale method. Okay, so that this is the range parameter of the Gaussian basis, and this energy. Then if we have a continuum state, then continuum state is decaying to some threshold. However, if we have a resonance state, then resonance state should be stable with respect to the range parameter of the Gaussian basis function. For example, I will show you just an example. This is a Isotope model, and you can see this is alpha, and this is energy. And you can see just dotted. Dot mean is an eigenvalue. So then you can, for example, if the alpha equal 1, then after diagonal Hamiltonian, we can get this line, the eigenvalue. And then we use the many alpha, then many times diagonal Hamiltonian, then we can get this eigenvalue. Then plot it, then if we have a resonance state, then resonance state should be stable with respect to the scaling parameter alpha. However, we can see that continuum state is decaying to the some threshold. Okay. So then what about hydrogen 7? Now, and I will show you this Jacobi coordinate where we scale. Now here, this is a triton, okay, plus NN. Then here, we scale to this small s direction and rho direction. In this way, we scale to the alpha for this coordinate. Then, and we just scale to the alpha equal 1.2 to 1.5 or something like that. And I diagonal Hamiltonian many times. Then this is my result. In the case of the V3 equal 8 femtometer and the V0 equal -3 MeV. And then this is scaling parameter, and here is the energy with respect to the triton plus 4n breakup threshold. So you can see that here we have a stable energy, okay? And then from this factor figure, then we can see the energy equal like 8.8 MeV, and then we can see from this avoiding energy, we can estimate the gamma. Then from this avoiding crossing, now we can estimate gamma is around 3 MeV, okay, like this. So then using this real scaling method, now we summarize that this my result of the hydrogen 5 together with, so this hydrogen 7, like shown in black point. Then this value is a value of the TNN 3-body force, okay? And also here is this value is a 3-body strength. In the case of B3 equal 8 femtometer. Then you can see here is also a result by mass, and which is also we are good agreement with the data of the hydrogen 5. Then in this case, what is the energy of hydrogen 7? Here it is. That means that in this case, the energy of hydrogen 7 energy should be the 9.5 MeV with respect to the t+4n breakup threshold, and gamma is around 3.5 MeV. So in this way, our predicted energy of hydrogen 7 is much higher and broad decay width. Okay, so now finally we summarize of the hydrogen isotope according to our calculation. You see, and this is the hydrogen 4 and 5, and then these are in good agreement with experimental data, and these two are our prediction. And I just show you the energy of hydrogen 7. This means the energy is around 9.5 MeV and decay with much higher, broader. And also I calculate hydrogen 6 is a little bit higher and decay with a little bit so broader than hydrogen 7, like this. Okay, so let me summarize. Now assuming that now ER of the 1.9 and gamma 2.4 for the hydrogen 5, then our calculated energy of decay width of hydrogen 7 are about 8 to the 9 MeV and decay width around 3 MeV. Okay, that is much higher than the hydrogen 5 plus 2n breakup threshold. Okay, now as mentioned before, this experiment was done at RIBA factory recently. So now this analysis is ongoing. Then I'm really waiting for the future experimental result. So if our result of the hydrogen 7 is in good agreement with experiment data, that to me, we could conclude that, okay, you can see, maybe hydrogen 7 is the end of hydrogen isotope. So we could not measure the hydrogen 9 because maybe if we have hydrogen 9, it's so far away with respect to the hydrogen 7. So therefore, we would say this is our prediction. Hydrogen 7 is a limit of the heavy hydrogen isotope thing. Okay, so thank you for the attention.
Do we have questions for our speaker?
Thanks for the nice presentation. When you calculated the width of your state, you took the first avoid crossing,
Yes.
but in the end, okay, yeah. It seems that you have another avoid crossing.
Yeah.
And why you choose the first one, not the second?
Here is so just I try to calculate, but here we decay into another threshold. So therefore, I try to see that where we go, like this. So therefore, here is broader than just we go to the keep hydrogen 5 plus n breakup threshold. But here is another decay. So therefore, now we want to know about the decay width to going to the hydrogen 5 plus 2n threshold. That is why I measure that this value.
Okay, thanks.
Other questions?
You use the Minnesota potential for the neutron-neutron interaction.
Yes.
There is a dependence on this force you can change for, there are several models, for example,
Yes.
Gaussian or other simple models. There is a dependence, or the results could be stable against using different neutron-neutron interactions.
In this case, is Minnesota potential scattering length is so the almost in good agreement with experiment data. So therefore, now I use the Minnesota potential, but also in the future I would use the, for example, every 8N potential. But so the quality, quantity is almost similar. That means the hydrogen 7 calculation is much higher the energy position, I guess, even if we use the NN potential. Different one.
And, I didn't see very well the neutron triton potential you are using.
Yes.
Which because I didn't see.
Yes,
Yeah, it suggested to calculations we have done for neutron triton scattering using four-body calculation for multi-tachyon potential, because we are limited by the model. We are not able to use tensor force, so we are not able to use realistic calculation results. So we were fitted for something which is doesn't require tensor force.
Which is the neutron triton potential? Is there? I don't.
This one.
It's a Gaussian.
Yes.
Ah, it's a Gaussian.
With
Here
some
you can see.
operator forms.
You can reproduce that.
This.
Okay, perfect.
Your Gaussians, you use a lot of Gaussians. Do you have any linear dependence issues, and do you choose them stochastically or by a deterministic algorithm?
So that means which potential you mean that? This one?
I'm talking about your basis set.
You mean that so basis function? You mean that?
Yes.
So then so yes, I use the so Gaussian basis function, and then.
Oh, they're stochastic? Did you
No,
say?
just so.
Oh, deterministic algorithm.
Yeah, just so I use the geometric progression. That is why I have a many and basis function. Currently 56,000 basis function. But now, you know, I can use a very powerful supercomputer. Then so that I have no problem for that. So even if we use such kind of many basis functionality.
And I was also wondering, did you only do one symmetry that you're pretty confident is the lowest energy?
And for the hydrogen 7, you mean?
Yeah, yes.
Yes, so now I try to calculate, try to find some, so in this case, I couldn't find anything for low. Yeah, in this case, unfortunately, so I couldn't find any lower energy.
You looked at other symmetries too, you're saying? Or you only did this one symmetry?
No, I tried to change many basis function. Then I tried, but so never.
No, but that's for one symmetry. So
Yes.
I'm asking, did you try any other symmetries, J and parity?
You mean so another J pi?
Yeah.
Yes, so then the J 1 plus the lowest one, but another one is much higher, yes.
Here?
Does your NN interaction reproduce the P-wave phase shift?
So you mean the triton neutron, you mean?
The neutron, triton neutron.
Okay, I will, okay, let me think. This potential?
Yeah, but you take it from Malfetion. Does it reproduce the P-wave phase shift, Malfetion?
Yes, so this is also calculation for the P wave like this.
Yeah, the problem is you have the splitting of P-wave when you have a tensor form. Then it's indicating that
The online.
okay. So the problem that for realistic phase shifts, you need a tensor force. So you have the splitting of the triplet P waves, and so, but here we used multi-tachyon because it doesn't give the tensor splitting, and multi-tachyon gives kind of efficient description of neutron triton scattering. Pretty okay. The cross section, it goes quite well through experimental data, total cross section. Of course, the differential observables, they are not good.
You said that complex scaling is too difficult for the five-body.
Nowadays, yes.
Okay, so but for the real scaling, how do you get the width?
Yes, so that's I use that real scaling method for the just so yes.
For the position?
Yeah, position for here, then avoiding cross section. Then so this is not accurate, just estimation.
Okay, so you can check with the complex scaling?
In the case of the three-body model, then I would, yes. And but we have a problem. In the case, even if we try to use this real scale method, for the narrower case, we could get like this. However, if this energy is a broader case, I couldn't do that. Yeah. So very fortunately, we could have this avoiding cross. So therefore, just accidentally, we could estimate this decay width. Of course, so that here, in order to use the complex scale method for five-body problem, we need more memory, and I need the CPU power. So then also this is challenging, and in the future I try to use the complex scaling method for the five-body problem. But now just so I try to calculate such kind of thing, because now the interest is whether or not the hydrogen 7 exists as a resonance state or not. So therefore that's this interest just I apply to this method, the hydrogen 7. Like this.
Thank you.
Further questions?
Well, it's not a question, it's just a comment.
Yes.
Because Emiko mentioned several times the experiment. So it's one experiment we did at RIKEN. And yeah, I wanted to say that before the experiment and before the calculation, there was a general belief that the hydrogen 7X is very low in energy, very close to threshold. And so during our analysis, we were puzzled not to find resonances at low energy. And during their calculations, they were puzzled not to find resonance at low energy. And finally, our results are not ready yet. We are testing some things, but our preliminary conclusion is that the ground state is at very high energy and is very broad. So we were quite happy to cross-check that we are puzzled equally, but that the calculation and the experiment seem to be in agreement. So yeah, so maybe we are both equally wrong.
All right, well, we just watched the scientific method take place then. That's wonderful.
Another question. I am still thinking to the neutron triton potential. Has some sense to some Coulomb try the proton and the proton and the phases. This has some sense to check.
From four-body calculations, we have also good neutron triton phases. But the problem is that from the method point of view, to apply this realistic potential for, let's say, neutron triton, at the moment we were not capable due to numerical limitations to use tensor force in this calculation.
No, these are probably there are places for proton and neutrino that you take your potential n triton, sum the Coulomb and make a to do the calculation for proton using string with the same potential plus Coulomb. I don't know if this does something.
I don't think so.
Check.
Yeah, it's you produce the phases, so it's
Okay. All right. One more question, one more comment.
On this hydrogen 5 and hydrogen 7,
Yes.
can you estimate the effect of the size of the triton core?
Triton is now frozen. So
Yes, I understand, but it has a dynamics. I don't know if this is too large. I mean, the overlap of the neutrons in the
you
is small.
okay, so that means that Triton 2 neutron of the inside of the hydrogen 5. Okay, I didn't calculate because this is a very broad resonance state. Therefore, it was difficult to get the wave function because this is a resonance state. If it's a very sharp resonance state, then we can get, for example, here is so we have maybe if we can get one plot, maybe we can do. But so this is not accurate wave function. It is okay because continuous.
All right. I said last one, but we'll give it to Nir. We'll give it.
What can we deduce about the tetra-neutron possible resonance in view of your calculations and the data we have on this hydrogen 5?
You mean that in the tetra-neutron state, if we have something resonance state and what's happening hydrogen 5, you mean? Okay, strongly bound. That is why first, after tetra-neutron state calculation, then we quickly go to the hydrogen 5. And what's happening if tetra-neutron state has some enhancement, and then we just apply to this calculation, the hydrogen 5 together with Rimas. Then we found strong bond. Yeah.
Okay. Well, let's thank our speaker again.